We are privileged today to welcome Professor Josh Tenenbaum, a professor of computational cognitive science at MIT. He is a research investigator at MIT's Center for Brain, Minds, and Machines and the Computer Science and Artificial Intelligence Laboratory, CSAIL. Josh's research straddles cognitive science and artificial intelligence. His goals are to reverse engineer human intelligence and to build machines that behave in a human-like way and have greater use for society. There are many accolades I could mention. Allow me just to highlight a few. In 2018, R&D magazine named Josh their Innovator of the Year. And in 2019, Josh became a MacArthur Fellow. He was cited as one of the first to develop and apply probabilistic and statistical modeling to the study of human learning, reasoning, and perception, and to show how these models can explain a fundamental challenge of cognition, how our minds understand so much from so little so quickly. Today, we can look forward to an exciting talk by Josh, so I'll be expeditious and hand it over to him. We have 80 minutes for the talk and questions, and after Josh finishes, I'll be looking for questions in the chat, and if you want to ask one verbally, just raise your hand in Zoom. So over to you, Josh.
Okay, thank you. Thanks, Unime. Can you guys hear me okay? Great. So it's a great pleasure and honor to be able to speak to you. I wish we were all in person. I hope to be able to attend GECCO in person another time. It's actually long been a goal of mine to come to this conference, though I've never been. But I've long followed and been inspired by the work in the community, especially people who are interested in evolution from both biological and artificial angles. And I think like many people, some of the work that was cited before in evolutionary computation and genetic programming, for example, Ken Stanley's work, some of Unime's work, Lee's work, the idea that learning isn't just, say, tuning parameters in a big system with lots of numbers like a neural network, but learning is some kind of operation over symbolic code, and all the ways that that might come to us through adaptive processes on different timescales. As you'll see in this work, that's something I've been deeply interested in and really only just starting to grapple with here, and we'll come to that towards the end of the talk. The goal of the research program that I and my colleagues have been working on for a while now is to try to understand where intelligence comes from, its nature, its structure, and its origins in the human mind and brain. To understand it in engineering terms, so we like to talk about reverse engineering, which means fundamentally it's a scientific project, a cognitive science project, where our goal is to have theories and models that are expressed in the same terms we would use to build intelligent machines. And then there's an engineering side, which is either a proof of principle or actual practical applications that where we try to put these insights into action to build more human-like forms of intelligence in machines. And I hope you'll see in today's talk both the science and some of the engineering aspects of the research program. Now, there's many places you could start in trying to understand why this is compelling and what we're trying to get at here in our particular approach. But where I usually like to start is to look at today's AI technologies, which are, not just to the people who actually make them, like many of you, but to everybody now in our parts of the world. AI is here in a big way in technologies that do things that we used to think only humans could do, and now machines can do them. But I think it's fair to say that we don't have anything like real AI in the sense of what the founders of the field were looking for. We don't have any general purpose, flexible intelligence that can do each and every one of these things for themselves, right? Today's AI technologies do one thing, and they're built at great cost and hopefully great care to do just that one thing. But there's no general sense of just anything that any one of our minds can do to grasp these problems for ourselves and get ourselves to do them. So why not? What's the gap? Well, again, there's many gaps, but where our work launches off is by recognizing the difference between one component of intelligence, which is you could call pattern recognition, function approximation, the target of machine learning, right? Where today's deep neural networks, but a long tradition of machine learning technologies has really advanced and made fundamental insights, both in terms of basic science and math and practical technologies. But consider all the ways that intelligence goes beyond pattern recognition and approximating functions from data, all the activities of modeling the world. So that means explaining and understanding what we see, not just finding patterns in it. It means the ability to imagine things that we've never seen, maybe things that nobody's ever seen, and then set those as goals and make plans and solve problems to try to make those things real. Or thinking about learning then as building new models, learning from both our successes as well as our failures, and learning not just individually, but sharing our models through language and other means, communication, so that knowledge can grow socially and culturally. So all of these activities of modeling the world, this is the heart of human intelligence that we're trying to get at. Now, we're very far from having AI that can get at this, and I think you'll see many common themes with Melanie's talk later on in the conference. But we are starting to make interesting progress, I think, and important progress that's informed by thinking about human cognition. And to focus in on one example of an AI technology that, again, is starting to be everywhere, where I think you can see the motivation for the particular work we're doing, think about autonomous driving. Okay. Um, by some estimates, this has been a target of at least $10 billion of spending, maybe $100 billion of investment, and it's been a serious project in industry for, I'd say, well over a decade, and within research for several decades. And we've made a lot of progress, right? Tesla, for example, just announced the latest version of their quote full self-driving mode. And I recently am visiting my father and drove in his Tesla, just the other day. It's quite amazing what that particular company has accomplished, as well as a number of others. But here I'm highlighting from a recent article in the New York Times, which starts off with a focus on Waymo, the Google or Alphabet self-driving unit, and some of the challenges that this industry has been grappling with, not just this year, but for the last few years and for more than a decade. As the article points out, um, there are so many things that can make the computer vision or sensing systems and control systems go wrong in autonomous driving. For example, spring blossoms can make your self-driving cars get twitchy, or soap bubbles, or road flares. There's so many things out there that these robots have to learn to grapple with. It's not just the world of objects, so many different kinds of things that could either be things you want to avoid or things you should learn to not be afraid of if you're building a self-driving car, but also the world of other people. As the article says, self-driving tech is not yet nimble enough to reliably handle the variety of situations human drivers encounter each day. It can usually handle suburban Phoenix, which is where the Waymo has been testing their cars, and where it basically never rains and basically nobody is ever walking. But it can't duplicate the human chutzpah needed for merging into the Lincoln Tunnel in New York, or dashing for an off-ramp on Highway 101 in Los Angeles, where, if you're not familiar with those cities, cars are jostling and have to really understand who's going at which point. Okay. Not to mention many other countries. Okay. Um, so what's missing here, right? Well, what is it that allows any teenager to get behind the wheel of a car? And if you're in Europe, it usually takes many hours of training, or a number of hours of quote training before you're legally licensed to drive. In the US, you can take a test and basically get behind the wheel the next day. And you're not a fully proficient driver. But even, I don't know if some of you have remembered this when you were a kid, but in the US, we also have a funny way that not just teenagers, but even kids who are just 5 or 6 can get behind the wheel of a car in what's called bumper cars, right? A sort of amusement park ride where you have an electric powered car and you have a little wheel, and your job is you can go around in a track and you can bump into their cars because there's a rubber bumper. You can turn, you have an accelerator. That's about it. I remember loving this kind of thing. You don't even have to have a driver's license to be able to understand, in a sense, the same kinds of things that we are still spending billions of dollars and years trying to engineer into our AI systems. It seems like there's something fundamentally different between how a human can just get behind the wheel of a car and understand what's out there and what other people, drivers or pedestrians, are doing, and the systems that are based on machine learning. So what is it, and how can we capture it in engineering terms? It's amazing, but it's not magic. What is it? Well, the focus of the work that I'm going to be talking about here is this idea of the common sense core. This is a particular notion of common sense that is influenced and developed by researchers in a number of different fields, but most especially in developmental psychology. Researchers like, for example, my colleague at the Center for Brains, Minds, and Machines at MIT, Elizabeth Spelke, although Liz works at Harvard, but we're part of the joint center and we do a lot of work together. But Liz and many others who study infant perception and cognition have found that from the very earliest ages that you can look, so for example, experiments with 3-month-old babies, you can already see that humans don't just find high-level patterns in pixels when they perceive the world, but our thought is structured around a basic understanding of the physical objects and substances that are out there, and intentional agents, that might mean human or other things, that move with goals and make efficient plans. And the interactions of physical objects and intentional agents, or what you might think of as knowledge systems that are sometimes called intuitive theories, abstract systems of concepts and principles, somewhat analogous to, say, the concepts of actual physics and psychology, but intuitive versions inside each of our minds and brains. These systems are not just distinctively human, they are shared with a number of other species, mammals, some smart birds. It's not even clear yet the extent to which they're shared, but widely shared. Though they're extended and enriched massively in humans because of how they support language and how language then builds on them and allows culture to dramatically amplify and extend, for example, our understanding of the physics of the world. When you study the brain, you can see that they're implemented in functionally distinct brain systems whose architecture is largely there at birth and before birth, because the brain wiring, which is set up for the first 9 months of gestation, is what sets up these systems. And they're really the glue of cognition. They're the bridge between perception, language, reasoning, and planning, in a sense, the output of perception, and then the substrate of thinking, and provide the basis for the plans we make to actually act in the world. So the research program we've been working on is to try to understand how these systems can be realized computationally. What does it mean to have an intuitive physics or an intuitive psychology that can be grounded in perception? And then to study them quantitatively in human behavior so that we can really test our engineering models, to understand how these systems can work in neural circuits. That's not something I'm going to say very much about today, except to just point to a little bit of early work on that. And then maybe most interestingly, to talk about how they're built through evolution, development, and learning. And again, I think here's where the greatest point of contact is with the Gecko community, although it's really just the beginning of, we're really just the beginning of that project. But I think it's an old project. It's maybe the oldest idea in AI that we could get inspiration for how to build machines by looking at how the human brain and mind develop. For example, Alan Turing, in one of the first papers on AI, the paper that is most famous for introducing the Turing test, he also introduced the idea that if we're going to build a machine that could pass the Turing test, maybe the best chance of doing that is not to try to jump right in with the adult human brain, but to start off building a child brain and then teach it like the way we teach children. And why? Well, as Turing said, because presumably the child's brain is much simpler. It's something like a notebook as one buys it from the stationers, with rather little mechanism and lots of blank sheets. Right? This is the idea that is, in some sense, the oldest idea. But if we've learned anything from now, it's that, in a sense, that blank slate idea, right, is not right. So I mentioned the work of Spelke and a number of other developmental psychologists who I'm very lucky to know and collaborate with, like my MIT colleagues Rebecca Sachs, Laura Schultz, or Alison Gopnik at UC Berkeley, for example. And they've famously articulated ways that the starting state is much more structured than just a blank slate. So this is Spelke's idea of core cognition. And I'm going to talk in this talk in a little bit about how we capture this with a slogan on our end that we call the game engine in your head. And also learning is more than just sort of soaking up knowledge as Turing articulated, but something much more like an active sense-making process. The idea of what's sometimes called the child scientist, as Allison has articulated, and as Laura Schultz has pursued in her work, studying the ways that we don't just um, find patterns in data again, but we make theories with concepts and principles, something like a scientist, and we test those theories by doing experiments, often being interested in how the theories go wrong just as much as how they go right. The experiments that children do, well, that's what we call play. But just like a scientist playing around in the lab, a child playing around in the crib may be the source of our best ideas. And I'll talk about how we're trying to start to capture this at an algorithmic level with something that we sometimes call the child as coder or the child as hacker. By hacking, we mean the good, cool kind of hacking around MIT, but more on that in a bit. So we start off with looking at what is the starting state, and this of intuitive physics and intuitive psychology. Now, I'm not going to show you. I'm going to show you a couple of videos of 1.5-year-olds, not of 3-month-olds, because 3-month-olds don't do anything, and it's not that easy to appreciate what they know. Although with the brilliant experimental designs of Spelke and colleagues, we are able to get some handle on what they understand. But look at, for example, what this kid is doing when they're playing with toys in their room, stacking up blocks or stacking up cups. And think about what it would take to get a robot to do the same, to be able to grasp the objects, not just physically, but in their minds, to make the kind of plan that you can see this kid making, which is roughly to make a stack of 2 and put it on that stack of 3 in order to make a stack of 5, to debug the plan in all the ways that are actually necessary when you're acting in the world and you don't have either perfect motor control or perfect grasp on the objects. We've made a lot of progress in robotics, but we still don't have any robots that have this basic common sense understanding of the physics of objects and what you can do with them. Or on the intuitive psychology side, consider this video that isn't just a YouTube classic, but from a famous experiment by Felix Warneken and Michael Tomasello from more than 10 years ago. Here is another 1.5-year-old who's the kid in the back. Warneken is the experimenter in the front. And the kid is watching an adult do something that they've never quite seen before, somewhat unusual action. But still, he's able to figure out what this guy's doing and even how to help him. When the adult stops, the kid, reliably, not all the time, but more than half the time, comes and does something like this, opens the door and allows the adult to achieve his goal. Watch it one more time and think about what has to be inside that kid's head. In some sense, he truly has to read the adult's mind to figure out what is his goal, because it's not just a stereotyped action. From how he bangs the books into the wall to understand the constraints that the door poses, and possibly what is a possible goal and some kind of communication. He steps back, and my favorite part of the video right here is when he looks up and makes eye contact and then looks down at his hands. It's as if to say, to show us, and maybe even to show the adult, I think I know what you're trying to do. And if I do understand that, then I think I know what you're going to do next, which is move your hands and put the books on the shelf. Again, if we could build robots that had even this level of common sense theory of mind or intuitive psychology and the ability to be helpful around the house or in work environments, it would be quite amazing. So we want to start off by seeing if we can capture this 18-month-old level of common sense physics and psychology. And we're doing that by building computational models that fill in the sketches that you can see on these slides here. These are sketches in some sense that could describe actual physics or actual psychology, but we mean them to describe the models inside these kids' heads of how the underlying state of the world changes over time. That's physics, and gives rise to perceptual observations, something like a process of graphics. Or on the right, that could be a model of how minds work, but for us, it's a model of how kids might think minds work. Okay, an agent takes actions in the world which are the result of beliefs and goals through a planning process. They act on the world, they change the state of the world and their own state in it, perceive new things and update their beliefs, and that loop continues. And there's experimental evidence, I'm not going to show you the experimental details with kids, that the mental models of even young children have all of these components. So our goal is to try to capture these in computational terms, and then I'll show you how we test those models quantitatively with adults. And if people are interested during the questions, I could talk more about how you test them with kids. So how do we capture these kinds of mental models? Well, there's a few things we need, and I think hopefully you'll start to see where some of the connections come in to the evolutionary computation and genetic programming community. The approach that we've been taking is that to capture these mental models, we can't do them just with neural networks or with any of the standard AI paradigms. We need, in a sense, a new synthetic paradigm for AI that brings together the best ideas of the field over multiple generations. So not just pattern recognition and function approximation, but symbolic computation and probabilistic or Bayesian inference. These other two ideas, at different times of the field were considered the fundamental way to go. In the earliest days, of course, symbol manipulation, abstract languages for knowledge representation and reasoning were considered the heart of intelligence, and I think in many ways are still the best idea that anybody's ever had about how intelligence works in computational terms. Consider that we wouldn't have any AI methods, whether it's neural networks or probabilistic inference, or any real computer science without symbolic programming languages, compilers, and so on. Not to mention all of the formal mathematics that they build on. Or consider the idea that was the leading idea when I got into the field in graduate school in the early 1990s, probabilistic inference, whether in Bayesian networks or other graphical models, or the idea that we could understand intelligence as making good guesses about the underlying or unobserved causes out there from sparse patterns of observed effects. Each of these ideas, I think, has something hugely to offer, of huge value for both human intelligence and for any kind of human-like AI. And if you're not familiar with probabilistic programs or probabilistic programming, I encourage you to check it out, perhaps by looking at this tutorial in the probmods.org webbook written by Noah Goodman and colleagues, including me. Noah Goodman is a professor at Stanford. I'm sure many of you might know of his work. And together with Vikash Mansinga, in our group more than 10 years ago, we developed one early probabilistic programming language called Church. At this point, both Noah and Vikash, who's now a PI at MIT leading the probabilistic computing group, have developed what I would call a new generations of modern probabilistic programming languages like Pyro or Gen, which are really nice artifacts that bring together these different all these different ideas. They build on top of modern deep learning languages like TensorFlow or PyTorch, but they bring together powerful ways to express probabilistic generative models with programs, and then to do inference with a variety of inference techniques. So this is, to me, the toolkit that we need to capture these kind of models in engineering terms, and I'll show you a bit of how we're doing that. The next key step is to say, well, what kinds of programs, what kind of symbolic programs are we going to do probabilistic inference on? And use, for example, machine learning, neural networks, and others to either accelerate inference there or fill in the gaps of what we can't build symbolically and handle probabilistically. And here's where the game engine in the head idea comes in. So we take inspiration and practical input from the world of game engines, which again, I'm sure everybody here is at least somewhat, and probably many of you are very familiar with, these tools that were developed by the game industry that allow a designer of a new game to focus on, to automate much of the basics of a video game, and allow the game designer to focus on the story, the world building, the characters, without having to, say, write all of computer graphics from scratch, because the game engine handles that. I mean, not just graphics, but physics. So, for example, game physics is getting quite advanced. This is not even the state of the art, but a couple examples of game physics engines simulating multi-rigid body systems, including very complex systems like the big block of blocks and the wrecking ball hitting it, or particle systems for non-solid substances or soft bodies like cloth. And it's really remarkable how you can make these fast approximations to the way physics works, not to mention to graphics, the way light bounces off of surfaces that can run in real time or much faster than real time. There's also game AI, right? So AI systems which are not full AI solutions, but model simple processes of perception and planning for the non-player characters in the game. And our hypothesis here, or it's an inspiration and it's a working model that we know is wrong in many ways, but an interesting place to start, is that something like this kind of architecture is what evolution has built into our brains. This is a way to capture the core knowledge that Spelke and other developmental psychologists have found in young babies. It's important to contrast this with other ways that people, I think, are using game engines in AI these days, especially, for example, in reinforcement learning, where a game engine is like a simulation environment for training an AI system through machine learning, and then the system gets deployed in the real world with some kind of sim to real transfer. Here, the idea is that the game engine is a model of what's in your head. So, for example, when this kid here looks at this configuration of blocks with the toy bird on it and holds the ball in their hand and thinks, I wonder what will happen if I roll the ball forward, he can simulate in his head something about the rolling and the collisions and the way the blocks might fall. And how does that simulation work? Well, maybe something like running one of these game style physics engines forward in time and seeing in his mind's eye what happens as a way to evaluate a plan, possibly debug one, or maybe even as part of the planning process. So what we've been studying in our work on intuitive physics, for example, is how we can take a game-style physics engine and wrap it inside a framework for probabilistic inference, for estimation and prediction, and use that as a model, a quantitative, rigorous model of intuitive physics. So in work now going back 10 years or so, with colleagues starting with Peter Battaglia and Jess Hamrick, both of whom were in our lab at MIT, at the time. Now both of them are working at DeepMind, the AI company, which I'm sure you're all familiar with, um, and pursuing in different ways interestingly related ideas. But a number of us have in the field of cognitive science have been working on things like this since the first work that our group did here, using game engines for physics modeling, where we do things like this. We show people, for example, these configurations of blocks, think like the blocks in the game Jenga. And we might ask to make a judgment, like how stable are the blocks under gravity? You could make a binary judgment, they're either stable or unstable, or a graded judgment, like on a scale of 1 to 7, or you could make a more interactive kind of task. But I think however you do it, I think you'll all be able to see that some of these configurations are much more stable than others, like the ones in the upper left, whereas the ones in the lower right look like they should be falling over. And that's what we try to model. We try to build a computational model that lets you work backwards from an image to make an estimate of the world state and how it's going to go forward in time. So to just give you just a picture of what's going on inside these models, and I point you to the papers like the PNAS paper from 2013, if you want an introduction to how these kind of models work. You see an image, you see that as the output of a causal process, which can be captured with a probabilistic graphics program. So there's an approximate graphics renderer. You observe the output of it, and you want to make a guess at the input to it. The input is some kind of three-dimensional object configuration, like what's shown in the upper left here, up here. Okay, you could think of it as something like a CAD model. That could have approximations in all sorts of ways. In this case, I'm just showing wireframe representations of the objects, but the key is that there's some kind of 3D model, and it's also important that they have physical properties, because this representation is not just the input to graphics, it's also the state, the input and output for a game physics engine. So in this case, what this configuration of objects represents is a sample, a Bayesian posterior sample from an inverse graphics system, a system which uses various methods, which I'm not going to go into the details of, to make a guess at likely inputs to a graphics function which would produce this output. Just in high level terms, that could either work through a kind of top-down, let's say MCMC approach, where you do some kind of Markov chain over possible scenes to find one that fits the image well, or with high probability. That's a top-down process, which is reliable but slow. Or you can have a bottom-up process. You can train a neural network to invert that graphics engine with samples from the probabilistic graphics model, and that's pretty good if you're given typical scenes. It might need some adjustment from a kind of top-down loop if you go beyond its zone of training. But through either top-down, bottom-up, or hybrid means, we're pretty good at this point at being able to come up with a approximate sample from the Bayesian posterior on world states given images. And then we can take that and run that through our physics engine to make a posterior predictive sample. So we have an approximate representation of physics that says that might have to make guesses about the friction or mass of the objects, as well as the forces in the scene, but has a pretty good sense of that. And so we can run, it's not completely deterministic, but we can run that sample forward a few time steps and just see what happens. And here you can see most of the blocks fell. Here's another sample from that process, a different state estimate, and runs forward a few time steps and you get a different output. Now, importantly, right, the precise output of one of these samples is quite different from the other. But at the grain of intuitive physics, they tell you the same thing, namely, all or most of the blocks fell. So you could run, I hope it's plausible, just one or a few of these samples and make a reasonable guess. And that's what our system does. So here now I'm showing you a quantitative experiment where we show human subjects, for example, 60 of these towers as stimuli. I'm showing 3 here in the colored frames. And each dot in the plot on the left represents one of these towers. On the y-axis, I'm plotting the average judgment on a scale of 1 to 7 that humans make about how likely the tower is to fall or how unstable it is. So high means unstable. And on the x-axis, I'm plotting the average of a few of these samples in the probabilistic physics engine simulation. And what you can see is there's a pretty good correlation. It captures most of the variance, but not all. Okay. And I'm comparing that here with, in some sense, you could call this a baseline or an ablation model. This is a model that is, in some sense, more correct. It's the same physics engine that was used to generate the stimuli and that was the core of this model here, but it's without any sense of uncertainty or probability. So it has actually the ground truth state and the ground truth physics, in contrast to just making a guess as the system on the left does. You can see that it has the crosses here are error bars, and there's no x-axis error bar because it's just perfect. Okay? It just knows exactly how many blocks have fallen, whereas this one has to estimate the expected number of blocks that fell. But what you can see is that while it's a better model of actual physics, it's a worse model of intuitive physics. The correlation with humans is about 0.6 instead of about 0.9. And you can see it actually makes some qualitative errors like this red dot, and to a lesser extent, all these points here, which are way off the line y equals x. The red dot is the most interesting case because this is a stimulus which people think is the most unstable, highest up here. But actually, in the ground truth physics, it's perfectly stable. It's not going to move at all. And all these other ones are, to a lesser extent, other kinds of, call them stability illusions, all right? They look to people more or less unstable, but they're all actually perfectly stable. And I think you might be able to see what's going on here if you look at the red stimulus. The blocks happen to be perfectly positioned such that they are in fact not falling over. But if they were even just slightly off from their actual position, then they would be falling over. And as far as your perception and your intuitive physics go, you can't estimate their position perfectly. So effectively, in your probabilistic intuitive physics, they are always going to be a little bit off in perhaps slightly different ways. And we think that that explains why you have this kind of asymmetry, that there's lots of things in the world that one can make if you attend to it. And actually, a lot of art does this, physics-based art, where it looks unstable, but in fact it isn't. Okay, so hopefully this gives you some sense of how our models work, and also where the probabilistic part comes in addition to a simulation program. The same model, importantly, to really show why do we call this something like an intuitive physics engine or a mental model. It's not doesn't just do this one task, but it's an engine for reasoning about many different tasks, really an unlimited number of tasks. Anything you can simulate here, and any query you can make can be a well-posed probabilistic inference. So not just will the stack of blocks fall, but which way will they fall, or how far will they fall? Or what happens if, for example, the gray material is much heavier than the green material? So here you can see these two stimuli which have the same geometry, but the blocks are colored differently. And if you know the gray stuff is a lot heavier, then if I ask you which way are they going to fall, you'll make a different prediction. And our model does the same thing. And it does that because there's actually mass parameters or density parameters which can be changed in response to being told that the gray stuff is much heavier than green. Or if I see something which looks like it should be falling over, but it isn't, I can use the same model to make an inference backwards to infer, well, is the red stuff or the yellow stuff much heavier or much lighter? And that might explain why these scenes are surprisingly stable. I'll just show one more example and illustrate this with a little bit of a demo, because I want to highlight the ways in which this approach to common sense is quite different from a machine learning based approach. This approach can support tasks which you've had a lot of experience with, like will the stack of blocks fall, but also tasks like this one that I'm going to show you, which unless you've seen me talk about intuitive physics before, you've never done. So you have no experience in the sense of direct training on task, but yet in a completely zero-shot way, you can still do these inferences. So consider, in the case like this, what happens if the table is bumped hard enough to knock some of the blocks onto the floor? Is it more likely to be red blocks or yellow blocks? So if again, if we were all in person, this would be a great thing to just do interactively, but follow along with me. Okay. So what do you think in this case, red or yellow blocks? Everybody's going to say red, and there's lots of good reasons for that. There's just a lot more red blocks than yellow, for example. But consider a few other scenes and try to answer as quickly as you can. So how about here? Now probably yellow, red, yellow, 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 red, maybe, yellow. Okay. So I just gave 10 or so examples. I could go on all day. How are you able to do this in really an unlimited number of scenes just with red and yellow blocks, not to mention many other tasks like this that I could make up? So the way our model does it, at least, is just illustrated here with a simulation of one of these scenes inside a simple game physics engine. And we're also going to simulate a bump of the table. I'm going to simulate first a small bump, and I'll stop it there. Or here's a larger bump. And in each case, I'm stopping it after just a couple of frames because I want you to see that you don't have to run the simulation for very long to know what the answer is going to be in these cases, right? You can already see in both cases that it's all the yellow blocks and few or none of the red blocks. So you know enough to say yellow. right? Also notice it doesn't matter whether you simulated a small bump or a red bump, and for the most part, it wouldn't matter which way the bump comes, although it might make a little bit of a difference. So just one or a few simulations under different possible initial conditions. And also they don't have to be especially accurate, right? I mean, this is a very hard situation. I mean, if you actually were interested in the ground truth um, outcome, it's a very hard simulation to do with all the nonlinearities over any time period. But even just a rough approximation for a short time of just a couple of these simulations is enough to answer the question at the level of intuitive physics, and that's what our model does. And what you can see here with, again, the similar kind of scatter plot of human behavior on the vertical axis and average of a few model simulations on the x-axis, is that we capture almost as well, not quite, but almost as well, this judgment as we did the much more familiar judgment of how stable is the stack of blocks. And we do so with, no task specific learning or no learning at all. This model there's no learning at all of this model. It's just built based on sort of standard kinds of approximations for fast simulation and probabilistic inference. That isn't to say that humans don't learn key parts of their intuitive physics. There's some evidence that we do, of course. But I'm just trying to show for people who are coming from more from a machine learning background how much you can do and what you can do differently if you think about what might be built into a system that captures the general properties of the physical world and probabilistic inference on that. Now, in more recent work, we've been studying intuitive physics in all sorts of ways, but I'll just highlight one recent study from Kelsey Allen, Kevin Smith, and colleagues. Kelsey is now actually also recently graduated from our department, also at DeepMind. Kevin is a research scientist still in our group. And they've been looking at ways you can use the very same kinds of approximate simulation-based, probabilistic simulation-based mechanisms for intuitive physics to now put your knowledge into action to solve problems like, for example, one, I'm sure we've all grappled with some version of this. Say you're out camping and you realize that you forgot the hammer to pound in your tent stakes into rough ground. What can you do? Well, can you look around and see other objects that might double as a hammer? You might quickly rule out some of these objects as just not having the right physical properties to achieve your goals. You might consider at first some of the stones, maybe try this one for a little bit and realize, no, it's not going to work, and I might need this other one that has the right size and length and sort of lever arm properties. Okay, so people are very good at not only using tools that have been shown to us, but for flexibly adapting objects as means to ends. And we've designed a simple kind of game, which I'm illustrating here, what we call the virtual tools game. And you can find this and play this online and as well as read the paper, um, which is quite a little fun game in which people have to solve a simple goal of getting the red ball into the green region by using an object, dropping it into the scene. And that's all you can do. So it's a very simple kind of tool use phenomenon. But as you can see from these different displays, there's many things you can do with this. Many kinds of affordances, many kinds of possibilities for solving problems. And hopefully what you might also see is that people don't always get these questions right or these puzzles right the first time, but there's a very rapid kind of trial and error learning process. In just one or a few trials, people can typically solve many of these levels. So we want to understand how they do that. And um, we've introduced something that we call the SUP model, or sample simulated update, which has at its core a probabilistic approximate physics engine, just the same kind of thing I showed you before. But it starts off with a prior on the most generic kinds of affordances of objects. So basically just say, I don't know what to do, but do something that can cause contact between movable objects, basically. And then it tries out from that prior a few samples to see what might solve the problem in its mental simulator. And if it finds something that seems likely to, then it tries it out in the world. And if it works, the problem is solved. And if it doesn't work, it tries to learn from that in a certain trial and error way to update the prior using fairly simple kinds of policy optimization methods. And the result is that with just a few internal samples on each iteration and just a few then outer loop samples of the world, the system is able to solve not all, but many of these different levels in the game that we've explored. Here I'm showing the model's behavior against humans for 20 of these different levels. And I'm showing it in the form of a learning curve, where on the y-axis, I'm plotting cumulative probability of success after n trials, and on the x-axis, I'm plotting the number of trials. Humans had up to 10 trials, and were mostly able to get solve the problems, or sorry, up to 20 trials. And the model is usually given up to 10 trials, could be given a little bit more. And you can see that it does a pretty good job of capturing difficulty and even the learning trajectory. It also does a pretty good job of capturing the kinds of specific solutions people do, both what they start off with in the prior, as well as the solutions that they come to in the end. Here I'm plotting the model's first and final action choices with the colored clouds, and the dots are people's judgments. Okay. More recently, this has just been published last year in work that hasn't yet been published, but was part of Kelsey's thesis and is in preparation. We're building on top of this model to understand where what you might call sort of more high-level strategies come from. I mean, if we think about what we actually learn to use familiar tools like a whisk or a hammer, or think about a catapult. You saw in the demos before we were studying kind of catapulting. You can think of these as concepts of kinds of things you can do with kinds of objects to achieve kinds of goals. So they're abstract classes or concepts on objects, relations, and events. And whether it's catapulting that you see in a medieval castle, or the kind of catapulting that somebody could design in their kitchen with these implements, or the kind of catapulting that we saw in the tools game. In some sense, there's a concept in common, and the same might be true for hammering, whether it's with a hammer or a stone or anything like that. So what is it about the objects, their relations, and the event that can capture the abstract concept, let's say, of catapulting? Well, the way we try to capture that, we take that simulation-based model and we just replace the initial prior with a learned prior that is now learned across different instances of, let's say, catapulting, to capture the abstract concept. And here, the particular method we're using is based on a probabilistic grammar for symbolic concepts that describe objects, their properties, and relations. And in this sense, we're starting to move towards something that looks a little bit more like program induction or program synthesis. And we think that if you want to capture how you go beyond the things that I showed you before, which might be the sorts of things that other animals can look at. We're actually starting to collaborate with colleagues who study non-human primates to see to what extent they can solve some of those same kinds of levels. But if you want to talk about quickly forming a new tool concept, we think you're going to need some kind of higher level symbolic learning on top of that. And so we've built a system that can do that can learn, for example, a catapulting strategy that looks something like this, described in this case as picking a large tool, then choosing a wide object that's supported, that can be the basis of the catapult, and then finding the right region of where you have to drop the object in order to make that catapulting. And we give people, to test this experimentally, we give them a number of scenarios, maybe 5 or 10, of different kinds of catapulting, or for example, tipping or making a table. And then we test their transfer in either near or far transfer cases, so harder, more interesting kinds of challenges. And what we find is the model, people are able to learn and transfer these strategies in many cases, and so is the model. There are cases where humans don't always succeed, and the model actually captures both the successes and the failures. Some of these failures, like the tipping transfers, are not so much failures, but actually cases where both people and the model come to different strategies. It turns out that for the tipping problem, where there's, in the actual problem of tipping, I better go back to this so you can see it. There's basically a cup that you have to realize you can knock over onto the floor for the ball to hit the green thing. That's what's shown here. The ball is in the cup and you have to knock it over. But in the far transfer of the tipping level, we have something where you actually can't knock the thing over, but you can get it to tip by placing an object underneath. And there's two strategies. One for tipping is place an object on top to knock it over, and the other is put something underneath, and only one of those transfers. And interestingly, humans, depending on just where they happen to go in their learning, discover one or the other of these strategies, and so does our model. So I can't say this is exactly how people learn about tools by any means, but we're trying to take a step towards, another step from the basics of kind of simulation-based intuitive physics to more abstract kinds of reasoning about tools. With colleagues in neuroscience, I mentioned that one of our goals is to understand how these things work in the brain. And with colleagues in neuroscience, especially in Nancy Kamrischer's lab, we have found what we think is the putative location of the brain's intuitive physics engine. I'll tell you why the location or the network basis matters in a bit. But our interest isn't just where in the brain, but how. And how does this play into the broader architecture of intelligence in neural circuits? And the way we study this is we first try to localize what part of the brain is making these judgments, and then we ask what is represented there. So with Jason Fisher, who is now at Johns Hopkins, we initially localized this part of the brain by contrasting physics-based predictions with very similar other kinds of predictions. And then with other colleagues, for example, Sarah Schwetman, we found that this part of the brain seems to have an invariant representation of mass, or weight at least, such that you can show people movies that reveal the weight of an object in different ways, how it splashes, or how it depresses a cloth, or how it collides transfers momentum, making another object go in a collision or stopping a collision. Um, and the representation of whether an object is heavy or light seems to involve the same neurons encoding it in something like the same way across these different scenarios. You can train a classifier on patterns of brain activation from functional magnetic resonance imaging for one of these classes of stimuli, and it can generalize to the other. And in more recent work that's just been submitted, we can also decode stability, whether it's objects or people interacting with objects. So the very same thing that we started off studying, you can find an invariant representation in this same part of the brain. And as far as we can tell, not in other places, not at least in earlier parts of visual cortex. Now, the reason why the location is interesting is because this part of the brain, which is shown here, it consists of, if you look at my head, sort of parietal areas and um, premotor areas, a network of brain areas which many people have studied before us. We're far from the first people to study this brain network. And it's previously been characterized as as the network that underlies action planning as well as tool use, and also something like understanding others' actions. So if you've heard of mirror neurons, then it's roughly same kinds of areas are involved here as well. So there's a lot that we still don't understand about how the brain does intuitive physics, plans actions, or uses tools. But there's an interesting evolutionary story which is suggested here, right? Which you could conjecture as something like parts of the brain that maybe originally evolved to guide our own actions in the world. Um, and as I think those of you who either work in robotics or have follow robotics know, the idea of using physics to optimize the trajectory of motion is kind of the leading way to get uh, whether it's humanoid robots or legged robots, for example, to walk. So even just moving your body around in space seems to require some kind of model of physics. And then that very same circuitry can be adapted to understanding how to use tools, how to plan your interactions with objects, and even as we've shown in our work, how to make judgments about physical scenarios that you're not even interacting with, but yet you can still imagine what might happen next and what could be done. So that's all I'm going to say about intuitive physics. I'm going to just very briefly mention the intuitive psychology side, but before turning to learning, because I know of great interest to many of us here. But just very briefly, the same kind of idea of using probabilistic programs to capture how we mentally simulate causal processes in the world can be used to capture something that you can layer on top of intuitive physics for intuitive psychology. And again, inspired by robotics and the ways that physics engines have been used for planning efficient actions. So watch this video and try to predict what this woman is going to do or infer really what her goal is. There's 16 objects on the table in a 4x4 grid, and watch as she's moving and see if you can guess which object she's reaching for. Maybe around now, probably is around when you can see it. Here, let's watch it one more time. You may have an initial guess, but it's hard to be certain until maybe about now. Now notice right around then, on the right, you see this dashed line shoot up to the top. That is not data from an experiment. That's the prediction of one of our models, which we've been building. This is joint work with Tao Gao, Marta Kriven, and a number of other colleagues, and builds on earlier work from Chris Baker, who was in our lab, and Julian Hara-Edinger, and a number of others. And the general idea that we've been working on for a while here is that you can, and it's again very much inspired by work in neuroscience and psychology, showing that when people at least move around space like this, they plan in very efficient ways. They roughly maximize the efficiency of their action. And so we can build what's effectively an inverse planning model where we assume the agent is trying to maximize something like their reward minus cost, a simple kind of utility function, where the cost is actually like the physical cost of moving your body, and that's calculated by a robotic physics engine. The reward is some positive value for getting to your goal. And if you assume that the agent is trying to plan to maximize their expected utility, then you can work backwards and make a Bayesian inference about what is the most likely goal based on the actions at state you've seen up till now, based on which source of reward best explains their action in a sense, which source of reward makes their actions approximately utility maximizing. So that's a probabilistic inverse planner that observes the world state and actions and works backwards to infer their desire or their goal. And it seems to provide a way of capturing how we infer someone's goal in a very general way, because it doesn't just apply to simple reaching scenarios, but it can apply to these much more complex situations. And ask yourself how you figure out what this person is reaching for in a funny kind of constrained way, as well as what makes the other person in the scene look like they're trying to help them, right? What makes that scene look like helping versus this scene here, which is not helping, but kind of the opposite, right? Here, the woman behind the table is actually actively competing with or trying to hinder the man who's coming around the front trying to reach the object. She's trying to figure out what he wants and get there first. Okay. So these concepts of helping and hindering, these abstract concepts, we think the best way to try to formalize those is with a recursive multi-agent planning system where what it means to be helpful is not just to act to maximize your own expected utility in one of these planners, but also to take somebody else's expected utility as a positive component of your own expected utility and to take your expectation about their expected utility. In a sense, it's like the golden rule, right? Do unto others as you would want them to do unto you, or sometimes called the platinum rule extension of that. Do unto others as they would want to be done by. That's a very general formulation of what it means to be helpful. And these probabilistic multi-agent planning programs can capture that concept, as well as what it means to be the opposite of helpful if you just have a negative utility dependence. And if we want to understand how a kid like this kid here can be helpful, or how we can look at the scene and understand that he's being helpful, we think this is a candidate way to do it. So this is very much work in progress, but hopefully it gives you a sense of where this toolkit is going. Okay. So in the last few minutes, I want to talk about where does learning come into the picture. Okay. Because up until now, as I said, there was no learning. We're just trying to capture something about the starting state or the early targets of learning. Now, as I've already alluded to, one approach which has always been popular in AI, and in some sense, I think some people in the evolutionary computation community are very sympathetic to, is to say what we've talked about here should be the target of learning, but our goal should be to start with as little as possible, maybe nothing, and somehow build a system that can get to the state of knowledge. Okay? Um, I think that's a very interesting target if you're taking an evolutionary computation approach, because I think in some sense that the knowledge that we're talking about here is what evolution has given us, and I'd love to see this community and potentially collaborate with people who might be interested in using evolutionary computation to see how we could build this kind of knowledge. Um, in the broader world, there's a lot of people who are pursuing what I would call sort of more like deep reinforcement learning approaches using neural networks, and I think that those are, in a sense, they're also in a sense trying to recapitulate evolution, but it's different because they're not trying to do structural innovation. They're just trying to adjust parameters of an existing network. So I think one nice example of this is from Dan Yeaman's lab at Stanford and the work of Nick Haber. And they build a kind of a curiosity learning system that's also infant inspired, and a system which sort of jointly learns a curiosity model based on some notion of surprising yourself as well as a world model. And they show that it's able, with a lot of experience, to capture some very basic forms of infant object directed attention. But while I think this is nice work, I don't think it's the way it actually works in the infant brain, because what it's learning over a lot of time is things that infants already show much earlier before they can actively move objects around as this system does. So I think we definitely need something which is more like a biological evolutionarily informed approach. What we do in our work is we're not trying to capture what evolution did. We're trying to start with something like what evolution gave an individual child and capture how learning in a single mind and brain works, learning inside the game engine, Maybe learning to modify the game engine, because what evolution gives us isn't hardwired. We know the brain is very plastic. So we might be given a lot, but it still can be modified. And then use that to learn other things. So when you ask yourself, if what would it take, for example, to learn something like a physics engine? Um, well, if our intuitive physics is represented by some kind of simulation program, then our learning algorithm has to be a program that learns other programs. Maybe takes as input an initial program and modifies it, or builds it out of some kind of programming language. But that's the basic idea of learning that we're approaching. And then we might think, and again, I'm mostly pointing towards work very much in progress and in the future, but the goal would be to say, take what we see in the development of infant intuitive physics over the first, say, year of life. Here I'm highlighting the work of René Baillargeon and colleagues, who have done probably more than anybody over many years, but many others in this research field have tried to map out what aspects of physics infants understand at different ages. And there's big error bars on these numbers, but there's at least some kind of trajectory of development of understanding of intuitive physics. And we could ask, can we capture these different stages of understanding as something like different stages of a game physics engine? And can we have a learning algorithm that can modify the physics simulator in response to experience, or maybe modify the control strategies that are used to use that simulator to effectively um, predict in the world? Because there's significant challenges that come up there, but somehow modify the program or the control programs for the simulator. So I can't say we can do that yet, but that's what we're interested in doing, and we're making some steps towards that. But I think it's also important to frame this in the even larger context. It's not just about intuitive physics, but I think, if we want to say, can we build a model that could learn everything that a human learns in their lifetime, or that humans have built up collectively across generations? And to do that, I think there's really only one paradigm of knowledge representation and learning that we have. And again, it's one I think that many in this community are interested in, which is the idea that all of knowledge can be expressed as code. And then learning is whatever it is we use to make our code better, whatever processes we do. And that's many of them. So this is the idea that we've recently described for a cognitive science audience in this review paper from Trends in Cognitive Science by Josh Rule and Steve Piantadosi and myself, which was also appeared in 2020. It's called The Childish Hacker. And again, here we're referring to not the bad guys who break into your email and steal your credit card numbers, but the MIT notion of hacking, which is just doing whatever it is to your code or whatever artifact you're building to make it cool or awesome, right, with some intrinsically motivated goal. But we start off by reflecting, again, as many have, that across all these different domains of human knowledge, the best way we have to capture the form of the knowledge isn't parameters in a neural network or machine learning system, but is some kind of code, whether in an actual programming language or some other kind of symbolic representational system. And then we say, well, learning is somehow a search for making your code better. But to this audience, I don't have to tell you the message of the slide, which you all know very well, which is that in contrast to, say, learning in a neural network, searching in the space of code is just a much harder challenge. There's no nice geometry or topology even, and it's not even necessarily clear what the y-axis should be. So, right, for example, Ken Stanley's work that was mentioned earlier in the journal session, is about exactly that, right? So what we're interested in, which I think is, and here's where it's a little bit different from maybe the evolutionary approach. In evolution, which is really the only thing we know in the biological world that actually builds new systems of code, right? We know, or our best hypothesis is that it's a long, slow, and dumb process, which is somehow remarkably smart and sometimes faster than we might imagine. But there's also analogous processes, call them like human cultural evolution, which are the processes of coding or hacking, which could be smarter and faster. And these are what we think are our inspiration for when we think about learning. Not evolution, but learning in the mind of an individual or in a group collectively. So think about all the activities of programming, which go beyond just, say, what we do in machine learning, where we tune parameters, or in neural networks, or most standard machine learning, the things that are all the big companies are mostly investing in. But all the things that are more like structural program modification, whether it's adding functions, debugging functions, but also like refactoring, making a new library of code that is reusable, scalable, for example, applicable to other problems, or even writing whole new languages, or transpiling or rewriting something from one language to another, or compiling, or indeed writing new languages, domain specific or domain general, which express some system of thought. We think, looking forward, and this is, I think, a long-term vision for the study of learning in humans and human-like AI, we need algorithms that can capture all these different kinds of activities of programming if we want to build algorithms that are really human-like learning algorithms. Okay? So not just a kind of sort of more random evolutionary style search, but something like the smarter, maybe more Lamarckian, or even smarter kinds of goal-directed activities of human coding. Now, we're very far from that, and I can't say we've made much progress on this, but I think this is a goal that we should be working towards. But in the last minute or two, I just want to highlight another recent project from our group and collaborators, which is the work of Kevin Ellis and colleagues. This is a paper called Dream Coder, growing generalizable interpretable knowledge with wake sleep Bayesian program learning, kind of a mouthful. There's a version that you can read on arXiv, as well as a conference version that was just presented at this year's PLDI conference. And for those of you who know PLDI, you'll recognize this. This work involves bringing together all the ideas I've talked about here, probabilistic inference and hierarchical Bayesian models with symbolic code as the basic representation language, and even a neural network playing a key role, actually, that learns to guide the search for code, with some sophisticated techniques from programming languages and program analysis. Kevin Ellis was jointly advised by myself and Armando Solar Lezama, who's the other senior author of this paper. And he's quite an amazing former student. He's just graduated and is now just started up as an assistant professor at Cornell. And he really remarkably combined some of the kinds of techniques that you've seen from our group with sophisticated PL methods to build this system, which learns to solve problems in many different domains. I'm showing 8 of them here, each of which is expressed as basically a programming problem. And it's an inductive learner, so it's like in other kinds of program induction or inductive program synthesis. It takes a small number of examples of input outputs, or maybe just outputs, and learns to write code that expresses the mapping from the inputs to the outputs, or produces the output. And the key thing that this system does, which is somewhat original, is it doesn't just solve one problem and another problem, but it actually learns to solve problems better by modifying and growing its language. So it starts with a very minimal programming language, a general one, with minimal domain-specific components, and it learns over iterative time by solving first the simple problems in the domain, and then learning to solve the harder problems by abstracting out through a kind of automated refactoring the common elements of code in the simple problems that it solved. And then those become new components in its program library that now allow it to solve new problems that it couldn't solve before, because with that expanded library, the harder problems now become expressible with short code, so the search process has a chance of finding it. To illustrate, in a sort of standard list processing domain, where we might be given input lists of numbers as input and outputs, for example, we want to learn a sorting function from just a few examples. This problem is too hard initially. The system being given just sort of basic functional programming, like map, fold, and so on, it is not able to solve this problem. But over time, it solves first simpler problems of list functions, and then it builds up a library. This is just a glimpse of the learned library. So it builds a filter function and a max function, and then an nth largest element function. And it builds them by solving problems that have those functions as components effectively, and it discovers them inside the code through this automated refactoring. The result is that after about 6 or 7 iterations, now it can solve the sorting problem by writing a simple program like this, which is expressed in terms of one of the concepts that it discovered in this learned library. It's not the most efficient sorting algorithm, but it's very easy to state and understandable. It just says, for n equals 1 up to the length of the list, get the nth largest element of the input and put that into the next element of the output list. Okay, very intuitive algorithm, expressible in short, understandable code, which if you were to convert this back to the original language would look like this. This is that same program expressed in the initial primitives, and it's hopelessly complicated and not understandable, and it's so long you'd never be able to find it with the kind of search processes that this algorithm uses. But we're able to find it through a combination of library learning, which leads to effectively a compressed, tuned representation. But also, there's a neural network that learns to guide the search. And that's really important because as the library expands, the search tree width gets bigger. And in some sense, the search problem gets harder at the same time as it's getting easier because the depth of effective search is shortening. So this is where the wake sleep learning comes in. For those of you who are familiar with wake sleep learning, you might recognize it as a variant on an old idea, where there's actually two phases of learning and sleep that are somewhat analogous to the different phases of learning in human sleep. There's a kind of an abstraction phase, which is that automated refactoring where you extract out code components that are used to grow the language and compress programs found during waking. And then there's a kind of dream sleep phase where you imagine random programs and those are used to train the neural network, which guides the search. And those two kinds of learning the explicit declarative knowledge of the programming language and the implicit procedural knowledge of how to search, are really powerful together. And we show in the paper how they bootstrap each other in ways that they couldn't do on their own. So just to illustrate this on a couple of the examples, it's easiest to illustrate on some drawing problems. Like, for example, we start off with a logo type language. Remember, like turtle graphics, where you have only very simple drawing primitives like pen up, pen down, turn, and move forward, in addition to just basic recursive functions. And from that, the system learns to draw quite complex things, which are easiest to see when you look at its dreams. At the start of learning, it imagines random programs, and they're not very interesting because it doesn't know very much. But after it's learned to draw a number of things, and it's built up concepts like circles, arcs, spirals, and rotational symmetry, higher order functions, now the programs that it imagines are much more interesting. And they provide much richer training data for a neural network, which can learn. It's based on a convolutional neural network that looks at these pictures and learns to guide the code search. And the dreams provide optimal training data. They provide a kind of completely self-supervised training signal for the pattern recognition system. So it's a really nice illustration of how pattern recognition can play a role in intelligence as part of guiding a search for structured programs in also a system which is fundamentally a hierarchical Bayesian model, because the simulations come from, again, basically a probabilistic generative model for code, much like the other probabilistic code learners that I showed you before. So just to illustrate some of the other cool things which you can read more about in the paper, given, for example, textbook physics problems, the system builds a library of vector algebra concepts and then uses those to learn physics laws, including even sort of physics motifs like inverse square laws. And this is just to be clear, this is not really discovering the deep principles of physics. This is doing a kind of structured symbolic regression with equations from physics textbooks and so on. But the key thing is that it's not just solving one symbolic regression problem, but it's learning the motifs of vector algebra and physics that then let it solve new problems much more easily. Or given, for example, textbook intro programming problems from like a basic Lisp class, the system is able to start off with sort of the earliest kind of 1959 McCarthy style Lisp, car, could, cons, and Y Combinator, and build up actually a learned library of modern functional programming. So the whole sort of fold, unfold, map, zip vocabulary of modern functional programs is something that the system discovers for itself in learning to solve these problems. So with that, I just want to wrap up by looking forward. I focused here on the earliest stage of core knowledge, right? The 1.5, 0 to 1.5 stage. But I hope you can see how we're starting to build systems that can start to learn the programs that would actually guide the development of, say, intuitive physics, but also these kinds of interpretable, generalizable, scalable languages for thought could provide the basis when we also combine them with, for example, the exciting advances in natural language processing, systems that can capture the stages of human learning that go beyond that, in particular how we learn to read, to write, to talk to each other, and then use that to acquire all the knowledge that humans build over generations and over different cultures. This is the real scaling route to AI in the human way, and the real singularity happens when you don't just start off with the core state of what we call the game engine in the head and the ability to do probabilistic simulation-based reasoning on that, but the ability to build symbolic languages of thought on top of that. So do we have a system that actually captures all of human common sense and learns like children know. I mean, I think this is many, many years away and decades, but I hope I've shown you at least a roadmap of how we and others in the field are starting to go about this. I hope you've seen also some of the many possible connections to what the Gecko community is interested in, and I'll look forward to any time that we have for discussion, as well as other possible collaborations or other discussions that people might want to have after this. So thank you very much.
Oh, thanks so much, Josh. I think we all collectively would clap very, very strongly and very, very long. Unfortunately, we can't give that to you on Zoom, but I've seen some really interesting questions on the chat. And I'll also take questions if people want to raise their hands in the Zoom. I'm going to start with one from Stefano where is it? Cagnoni. Yeah. So he said, I remember Roz Picard. Well, actually, he said, I remember Professor Rosalind Picard about 30 years ago introducing the course on pattern recognition by quoting Doug Hofstadter. Phenomena we perceive to be magical are always the outcome of complex patterns of non-magical activities taking place at a level below perception. The magic behind magic is pattern. How do you substitute or extend the word pattern to update that quote and describe your research?
Oh, that's an elegant quote, an elegant idea, and Hofstadter I think has been inspirational for many of us. Yeah, I mean, I think in some sense you could say, like, I tried to highlight the limitations of what most people call pattern recognition. I think, and here I think I'm just kind of in a different way quoting Doug Hofstadter. There is a more general notion of patterns, which includes everything that we're talking about. So, neural networks or machine learning as it's conventionally practiced is what most people mean by pattern recognition, and probably most of what Roz taught in that class, if I remember myself. But symbolic rules are other ways of expressing patterns, and the things that last system of Dreamcoder that I showed you learns effectively patterns in code. So if code represents a pattern in a problem, then if you have multiple pieces of code that solve multiple problems and they reuse some kind of computation, then that's a higher order pattern. And of course, when you talk about Bayesian inference and finding priors, that's also kinds of patterns. Like the strategies for tool use that we were talking about are effectively priors for a Bayesian learner to do rapid physical problem solving. Those are all kinds of patterns, I think. And if we want to view patterns as the fundamental principle of intelligence, that's fine. I think it's great. But what we need a computational toolkit that isn't just about the traditional ways that people have approached pattern recognition using, like, high dimensional vector spaces and linear separators and various generalizations of that, which are amazing. They can do amazing things, but which also involve the tools of symbolic computation, abstraction, as well as probabilistic inference. So you could view the entire toolkit that we're trying to capture here for reverse engineering common sense as just a richer toolkit for understanding what patterns are in the mind and how we might come to them. I think maybe that's the clearest I can say tonight.
No, that's a wonderful answer. Yeah, I think it's really patterns of behavior. Yeah. So I'm going to go on to a question by Max Buzdalov. He says, refactoring when sleeping and shaping search when sleeping. The next step is probably setting problems on its own and solving them, which might be asleep or an equivalent of self-reflection. Have you considered that?
Oh yeah, absolutely. And I mean, again, I think we've considered that, and there's much more to do than that than we do. I mean, in this paper, right? So the dreaming phase, there is a sense sometimes we feel like in dreaming we set problems for ourselves and hopefully solve them, or sometimes don't solve them, and then we wake up thinking like, oh wait, I know how to solve that problem and go back into it, right? So in some sense, the dreaming phase is actually doing that in our system as well. It doesn't just provide the training data for the neural network. It actually works better if the system generates a random problem and then solves it and trains the neural network to capture the patterns in its solution. And that actually is technically important. It breaks certain symmetries in the search. But the novelty is limited, right? Because basically the problems that it imagines for itself are just draws from this probabilistic grammar, which abstracts the code that it wrote in waking. So it's kind of like recombining elements of problems that it experienced in its waking life, which often is what some of our dreams are. But I think human creativity, whether it's in dreams or in waking life, where a lot of the most interesting problems that we create for ourselves are the ones we do in waking life. They just go much beyond that. And so that's just going to require, to capture the human ability to make problems for yourself is going to require an understanding of goals and the role that goals play in mental life that's much richer than that system does. I'll just point to, for people who are interested, the work of my colleague Laura Schultz, who I mentioned earlier for some of her work in understanding how children build their intuitive theories through play and experimentation. But what she's been working on recently is exactly this. And she's written a really nice review chapter of Child's Play and other papers recently with her graduate student, Junyi Chu. And what they're really trying to get a handle on the remarkable human ability to come up with problems for ourselves and what role that plays in thinking and learning. And together with Laura and others, I'm trying to understand that in computational terms as well. So you're exactly right to point to that as like one of our next steps.
Okay, now I'm going to try a live question. So Jürgen Branke, do you want to ask your question?
Yeah, thank you very much for this fascinating talk.
Thank you.
Kahneman has proposed in his book, Thinking Slow and Thinking Fast, that actually we have two ways of going about making decisions. Would you agree with that? What you have proposed, your simulation-based planning, basically, or finding the answers based on simulations, is an example of thinking slow, whereas maybe the deep learning is an example of thinking fast? Do these match together?
Yeah, that's a great question, and I think about that a lot. I think Kahneman is one of the brilliant figures of our field, and the points he makes in that book are important ones. But I think many of us in cognitive science, I think we would resist a simple dichotomy that says there's just two methods. There are trade-offs that humans seem to have, many different kinds of cognitive systems, and exactly how you map any of the models that we're talking about here onto those distinctions is not so clear. But you're right. That is a way that we are thinking about that. I would say it is fair to say that, for example, when it comes to um, a judgment of will these blocks fall over, the fastest thing you could do is just to train a neural network to just detect stability or something like that. And running a simulation is a little bit slower. It's not that much slower, and it's still, I think, fundamentally much closer to perception than a lot of the slow processes of thinking that Kahneman was talking about. But it has some of the same properties. You're right that, like, if you train a neural network to solve these judgments, I didn't show that, I just skipped that for time, but you can do that. And it has certain kinds of system one type of properties in that it's very fast, but it is not that robust, and it doesn't really know when it makes mistakes. Whereas the simulation is a little bit more robust, or sorry, is much more robust in terms of generalizing. But it also has illusions, like that stability illusion. So, to me, I still think of that simulator as actually closer to perception in system one compared to other kinds of, say, intuitive physical reasoning, where you actually express to yourself some concepts of like center of mass or balance, and you can show with other sorts of studies, as for example, the developmental psychologist Bob Siegler has shown, that kids, as they develop, they have something that's kind of simulation based, and then they learn some simple rules for how things balance, and they actually get confused because their simple rules aren't quite right, but they kind of go with those explicit reasons over their implicit things. And then as you get older, you learn to balance between these. So anyway, there's much to say, I think, about that topic, and I think it is right that for those of us who are interested in AI and learning, that isn't just based on like feed-forward neural networks or just the standard pattern recognition toolkit, that does more kinds of reasoning, whether it's through simulation or probabilistic inference or symbolic reasoning. There is a lot of inspiration in what Kahneman talks about in that the interplay of multiple systems of cognition that should inspire us here.
Great. Well, unfortunately, we're out of time. We've gone a little bit into the coffee session. I want to thank you again, Josh. We really, really enjoyed the talk. It was a privilege to hear about your research agenda and how many achievements you have already in it. And we wish you the best of luck with all your goals in the future. And we will probably all follow them. And I hope you get some feedback from the evolutionary computation community that's useful.
Thanks so much.
For everyone,
it was really helpful, and I'd love to find ways of collaborating too, because I do think the evolutionary computation techniques and questions. I hope that people can see the synergies, and I'd love to follow up on that if people have thoughts on that. So yeah. Thanks.
Okay, and conversations can continue in Gather. I've put the Gather posting, the Gather link in the Whova chat for the session. So if anyone wants to continue, you can head over there. The Gather is open 24/7 anyway, so you can always head back later too. All right, thanks everyone.
Thank
I'll
you so
hand
much.
it back over to Bilal.